Start sharing the screen, children. I hope it should be visible to you in a minute or two. Yeah, it is visible, I guess. Okay, so good evening, children. Once again, it's great to meet all of you. Fine. So last class we were doing motion in a plane. That is a chapter that we are looking at. We looked at different aspects of vectors, right? So we looked at what is the representation of a vector, what are vector dot products, I mean, and scalar dot products we saw, and we saw vector cross product. We learned about the angle between two vectors. Okay, so vector is basically, it's a huge area. So we have looked at different aspects of vectors, and we have also solved some questions based on it. Some basic questions we have done it. Okay, so still we are left with some more concepts, and now we will move on to the, and then we will start solving the questions proactively. Now we have finished, as we are done with vectors. Now children, now that we are moving ahead, so we have some more concepts also which are there. Some overlapping concepts are there, plus we also have a few more topics. 2 to 3 topics are left behind. So positively we'll finish it, and then we will start looking at different numericals based on this chapter, motion in a plane. Okay, so the next topic which is lined up for today is, we have the concept of projectile motion. Okay, so that is what we will be looking at today. We'll be dealing with that. There are different aspects, children. Projectile motion is again a vast topic, unlike vectors. So is very important. So please ensure that you pay attention. Somewhere you're stuck, you can definitely ask. Okay, because this is little crucial as well as critical. Unlike vectors was little easy, it's easy to understand. So this one, there are different situations that we will be considering before we relate the equations in projectile motion. The first one, so I'll just put the heading. So for today, we'll be looking at projectile motion. Okay, so we have projectile motion. So first, we try to understand what is a projectile. All right. So we try to understand the basic term of what a projectile is all about. So here, projectile, I'll just give you a basic definition for projectile. Okay, a projectile is basically an object that is thrown with some initial velocity. You throw an object with some initial velocity, okay, upwards or against gravity. When you're throwing it, what happens? The object is going to be airborne for some time. That means it travels in the air for some particular duration of time. So then you call that object which is being thrown with some initial velocity as a projectile. I repeat, projectile is an object that is thrown against gravity with some velocity. It can be against gravity, or it can also be towards. That purely depends on the situation. So when you throw an object with some velocity, okay, in the air or in the atmosphere, so you call that object as projectile. We generally define that as projectile. Okay, so let's try to I'll just give you the basic definition for this. A particle, okay, a particle thrown obliquely in the sense some angle, okay, horizontal, thrown obliquely near the surface of the earth, near the surface of the earth, near the surface of the earth. Okay, just 1 second. Yeah, I'm back. So an object that is thrown and it moves along a curved path, and it moves along a curved path, okay, is known as a projectile. is known as a projectile. So you call that aspect, that object, as a projectile. For example, what about real life examples of projectile? A cannon being shot. Okay, a cannonball being shot from a cannon is an example of, you know, a projectile. And the path taken by the cannonball is projectile motion. Now, any other example? A bullet being shot from a rifle or a pistol is again an example of projectile. A football being kicked, okay, by a player is an example of projectile. A cricket ball, okay, being bowled by a bowler is again an example of projectile. So like this, you can give different examples. I hope you guys also know what a slingshot is, slingshot or a catapult. Okay, so we aim certain targets, and you are usually using it. So to hit a target, so the motion of the stone or the pebble using a slingshot is an example of projectile. So like this, children, you can give different examples. You can correlate to understand what projectile motion is all about. Okay, so that's the basic idea of projectile. Now I'll show you the diagram so to make things more clear. Okay, so children, this is the ground level. We have the ground level. What we are doing, I'm taking an object at a specific height. Say on top of this you have a small building. Okay, there is a building on top of the ground level. So imagine this to be your building. Now, an object is being projected from this point A of the building, which is a top point. Okay, and the bottommost point of the building, let me take it as point B, such that the height of this building from A to B, let us take this as H. Okay, H is the height of the building. Now, what I'm doing is basically I am projecting an object from point A with some initial velocity. So an object is projected from point A with some initial velocity u. So this is the object that is being projected. So what happens when it is being thrown with some velocity? This object will start moving. Okay, it starts moving like this, and eventually after some time it will reach the ground like this. So it basically travels a parabolic path, as you can see. So this path traveled by the projectile during its course of motion is called as projectile motion, and the object is basically called the projectile. So this object, we call it as projectile, and the path, you can see I have shown the path by using a dotted line. This dotted line represents projectile motion. Fine. So this is the basic aspect that you should be knowing. Okay, about what a projectile is and what projectile motion is all about. So H is nothing but the height between points A and B. Now say the projectile is landing at point, say let us call this point as C. Okay, this point we will take it as C. This distance between point B and C is called as the range of the projectile. So here we call it as range. So we will take it as x itself here for simplicity. So x is nothing but the horizontal range of the projectile. Okay. This is called horizontal range. So these are the different aspects that you should know for what a projectile is. The basic ideas now you know. Now let's try to analyze certain things here for a projectile. Now why do you think when a projectile is projected with some velocity, is going to come down after some time? That is because gravity is going to act at each and every points along this path, because Earth is having gravity and the projectile is being pulled downwards by gravity at each and every point of its motion. So at the bottom, gravity is going to act, and that is the vertically downward component, and the horizontal component that you see is your velocity component with which the projectile is being projected with. Okay, so these are the aspects that you must keep in mind. So there are two components. One component is the horizontal component and second is the vertical component. So vertical component, we will call this component as uy, and horizontal component we will call it as ux. So there are two components, children. Ux is called as horizontal component and uy is called the vertical component. So there are two different components that we try to study here for the projectile which is being projected with some velocity. Now let's write the expression for this. Okay, so here the vertical component we write it as uy. I just showed you. So by applying our equations of motion, we can derive the relations for this. Okay, from vertical component, so from vertical component of velocity, we can write uy, okay, is equal to, now at the bottom you know that gravity is acting, right? So therefore we can write uy is equal to g into t. So we can express like this. So uy term is equal to g into t. So you can express it as acceleration due to gravity into times t, because you only have gravity that is acting and no other force is responsible here. Only acceleration due to gravity is responsible. So uy is equal to g into t, we write, and it is positive because it is moving downwards towards that is in the direction of gravity of the earth it moves. So we write it as g times t. So we are expressing like this. Okay, so this is the corresponding relation. How this relation came? So I have written the relation directly. You all know that from first equation of motion, which we have already learned, first equation of motion, if I'm applying, you people know that v is equal to u plus at, isn't it? This is what is the relation for the first equation of motion. Now by using this relationship for the vertical component of velocity, you know when a projectile is projected with some velocity, okay, u component is definitely there, but after some time the projectile is going to go and fall down. It's going to reach the ground and final velocity becomes zero. So therefore final velocity term is not going to be there. It does not exist. So technically you can write down this as u is equal to g into t itself, because this term we are not expressing itself. The final velocity term is not expressed. Okay, so that's the reason you will get uy is equal to g into t. This is purely from the first equation of motion. So you'll put a is equal to g plus g here, substitute, and then you go for a rearrangement. So you will get this. Similarly, so this relations you should keep in mind. Similarly, for the time taken by the projectile, we will find out what is the time taken by the projectile to reach the ground. Now let's write that. Time taken by the projectile to reach the ground. So what is the time taken by the projectile to reach the ground? Let us try to analyze this. To find out this particular relation, what we are going to do, we make use of the second equation of motion. So from second equation of motion, you all know that s is equal to ut plus half at squared. So this is the relationship that you typically know. Now what is s? S is nothing but the displacement. So what is the height from which the projectile is being thrown? We already wrote the height as h. So in the place of s, you will substitute h is equal to ut. Even before it is being thrown, there is no velocity component. So 0, which is equal to half. In the place of a, you will substitute g. So half g into t squared. So you will get the expression like this. Go for a rearrangement now. you will get that t squared is equal to, you make t squared the subject. So you can write this as t squared equals 2h upon g. Okay. So what is t in that case? This implies t is equal to under root of 2h by g. So this is the time taken by the projectile to reach the ground when it is projected from a certain height. So like this you will find out, children, the relation. So this is the expression for time taken by the projectile. Okay, so like this you get the expression for time. Okay, so similarly, next we find out the expression for the horizontal range. So going back, you can see horizontal range is nothing but the x. The distance between B to point C is the horizontal range. So we wish to find out what is the value of x. So let us make use of again the equations of motion. This time we will make use of the third equation of motion. Okay, so from third equation of motion, so from third equation of motion, we all have v squared minus u squared is equal to 2as. So here, children, you will go and substitute. You know that final velocity is going to be equal to 0. So v is equal to 0. So you will go and substitute in the place of v 0. And here, as the displacement, that is s, is equal to height of the projectile. So you will take s is equal to h. So you can make use of this particular relationship. So s is equal to h. Okay, and what about u particular value? So here you have u square terminology coming into picture. So already we have found out the value of u also. Okay, so u is equal to gt, so which we have already found out and kept. Okay, now here instead of taking s is equal to h, we have to take s is equal to x. Why? Because we are talking about the horizontal component, horizontal range, which means the horizontal distance is what we are talking about. So therefore we will replace s with x and not h. So I am replacing s with x now. So this is x. So I will put x in the place of s. So once you are putting the value as s is equal to x and v is equal to 0, so go ahead and try to express. You get minus u squared is equal to 2g. In the place of s you will put x. So you will get x. Now going for a simplification, you will get x is equal to u squared upon 2g. So negative term, show the negative term as well. So minus u squared upon 2g. So you can find out the value of x in this particular aspect. Now what we do generally, the horizontal range that you have, we only show the magnitude. We want to find out what is the magnitude of horizontal range. So because we find out the magnitude, what we generally do is we take something called as modulus. So taking modulus. Modulus, children, you need not confuse. Modulus is basically operator which makes any value as positive. So modulus of horizontal range will make the value as u square upon 2g, and that's the value of your horizontal range. So you can find out the horizontal range using this particular relationship. Okay, so you can use this alternatively, you can use second equation of motion. So I will show both the ways of expressing. If you're using second equation of motion, then you can write s is equal to ut plus half gt squared. You can make use of this relationship as well. In that case, you will get x is equal to half g t squared. Okay, so because I am substituting the place of s, x again. Okay, now initial velocity component here, so you need to keep that in mind. Okay, so here even before it is being thrown, we don't consider the initial velocity component. Here, after it is being thrown, then you will consider. So depends. In terms of initial velocity, if you would like to write it like this. Without initial velocity, if you want to find out, then this formula is useful. So appropriately, you will choose the formula based on the situation, and then you will find out. So there are two ways of expressing the horizontal range. Both are important for us, okay, based on the situations. So we have two values for the horizontal range, okay, of the projectile. So now we have looked at the first type of projectile. So first type of projectile is now complete. We have learned if a projectile is projected from a certain height above the ground level, what is its velocity component, okay, and what is its time taken, what is its horizontal range. So all these three things have been analyzed so far. Now we are moving on to the next aspect, okay. We'll see what is the next aspect for the projectile itself, okay. So moving on, second type. A projectile projected vertically upwards. Okay. A projectile projected, okay, instead of vertically, we will make it obliquely because we are looking at oblique case. Projectile projected obliquely at an angle theta from the ground level, okay, at an angle theta from the ground level. So we'll see how this particular diagram looks. So we try to now relate this. So this is the ground level. So here, children, we are having a projectile now. So let me take a projectile here. This is a projectile. So this projectile is projected now with some initial velocity. So we'll call this initial velocity as u. And it is making an angle of theta with the ground level, like this. So this angle is theta with the ground. So this, you know that this is ground level. So with the ground, it makes an angle of theta. Then what will be the motion taken by the projectile? How will the path of the projectile look like? So we will try to see that, visualize. So when an object is thrown, it will reach a height and then it will fall down like this, okay. So it will take a parabolic path basically. So here you can see that after some time, the projectile is reaching some maximum height. So at this point, it is reaching maximum height. So let me mark this point as A. Let me mark the point from where it was projected as O. Okay. So if I drop a perpendicular from A on the ground, so this is going to give me the vertical height, the maximum height. We will call it as H max. Okay, the maximum vertical height attained by the projectile is H max. Okay. So H max is maximum vertical height attained by the projectile. Okay, attained by the projectile. And after some time, it's going to, you know, reach the ground also. So as soon as it is projected, it is reaching point A at maximum height, and then it reaches point, say, B. At B, it is reaching the ground again. Now, the distance between O to B is called your horizontal range, R. So R is called the horizontal range. R is called the horizontal range of the projectile. So this you must keep in mind, children. Okay. Now, based on this figure, what we are going to do is we are going to resolve the projectile, which is projected with some initial velocity, into both vertical and horizontal components. I repeat, we are going to resolve the projectile in both vertical and horizontal components. So how do we do that? So let us see. So here you have the projectile. Projectile is making an angle theta with the ground, you can see. So this component along with the ground level, this component, I'm using a different color to distinguish. So this component is called the horizontal component of your projectile, which is given as u cos theta. So horizontal component is given u cos theta. What about the vertical component, children? How do you find that? It is, so what is this remaining angle? If this angle is theta, this angle will be 90 minus theta. I hope you guys know, because total angle is 90. So this component, vertical component, will be u cos of 90 minus theta. I hope you might be knowing in maths, cos of 90 minus theta is sine theta. So you will get it as u sine theta. That is the vertical component. Okay. So u sine theta is vertical component, wherein u cos theta is the horizontal component of the projectile. Okay. So let me write it here. So u sine theta is the vertical component, and u cos theta is the horizontal component. So there are two components, vertical as well as horizontal components. Okay. Once you have identified the vertical and horizontal components, now we go ahead and we try to get the relations. So we'll see what are the relations that we try to get. Okay. So now, first one is the expression. So there are different expression, children, that we need to be writing here. So here you can see, after the projectile has been projected, it reaches the maximum height. So we'll see the expressions, children, directly, so that we can apply them for certain questions. So first one, what we are going to see is time of flight. First expression that we are seeing is time of flight. What is meant by time of flight? It's basically the time for which the projectile is in air. The time for which the projectile is in air, you call it as time of flight. Even before it touches the ground, for how much time duration soon after throwing it is remaining in air, or it is airborne, you call that as time of flight. So this time of flight is represented by the letter TF, capital T suffix F. So time of flight TF is represented, okay, by using the formula. We have 2u sine theta divided by g. So this is the expression for time of flight, okay, where u is the initial velocity of projection. You know that theta is the angle, and g is acceleration due to gravity. So this is for time of flight expression. Same way, let's move on to the next expression, the second expression. Next, we have the expression for the maximum height attained by the projectile. Maximum height. What is maximum height? Okay, so you can see with respect to the figure, point A is the maximum height. Okay, the vertical displacement, having maximum value is your maximum height. Vertical displacement having maximum value with respect to the projectile. So you call it as maximum height. So again, children, that is given by a relation. So there is a relation for maximum height as well, which is given as h max. Okay, so we have h max. So you can write that as h max is equal to u square sine square theta divided by 2g. This is the expression for maximum height of the projectile. Okay, so we have seen the expression for maximum height as well. Next, third one. So like this, you have the important relations which you should be knowing. Then you have horizontal range. Okay, horizontal range. What is meant by horizontal range? When you refer back to the diagram, horizontal range is the distance to the final point where it lands. Okay, where the projectile would land. That distance on the ground level, you call it as horizontal range. Okay, the horizontal distance. So we can say this as the horizontal distance between the initial point of projection, say initial point A and final point, I think we took it as B. Initial point I think was O, right? Let me change it. Okay, so it was O, I guess. So we'll put it as O. Between initial point O and final point B. So you call that as horizontal range. And it was given by the letter R. So R is equal to, it's given by the relation U squared sine 2 theta upon G. That is the expression for horizontal range. Okay, so this is the next relation that you must be knowing. Okay, children, so now we have seen the important relations for the projectile, which is projected from the ground having an angle of theta. So we have identified the relation for time of flight. We wrote what is maximum height, and we also related what is horizontal range. Okay, so these are the important aspects that you should be knowing. Okay, and when is this horizontal range going to be maximum? For what value of theta is horizontal range going to be maximum? Now let us try to find out. You know that sine value has maximum value, sine theta is having maximum value for 90 degrees, right? It ranges from 0 to 1. So sine 90 is 1, wherein sine 0 is 0. So when can sine 2 theta be equal to 90? You will have to think. So you want sine 2 theta should be equal to 90 degrees. Okay. Under what circumstances will it be equal to 90 degrees? When theta is equal to 45 degrees. Only then 2 theta becomes 90 degrees. Okay, that is, I'm only talking about this 2 theta basically. So in sine 2 theta term, when is 2 theta going to be 90? When theta is 45. So this is the condition for maximum horizontal range. This is condition for maximum horizontal range. Yeah, so this you should keep in mind, because you know that for theta equal to 45, you go and substitute 45 there. What happens to the formula, children? If you put 45, the value of R, if you see, you can see that R is equal to U square sine 90, 1. So you get R is equal to U squared upon G. So this is R max. That is maximum horizontal range. The formula gets simplified as U squared upon G. Okay. So this is about it, children. So now we have related certain important terms that is very important, that is necessary for solving certain questions. Okay. So with that, we'll move on to the next aspect of projectile motion. Okay. So here, what are the other aspects also? Let us see. Okay. Some important pointers also I'll give you. So here you need to note these points. This is important to keep in mind. Horizontal range will remain same. It remains unaffected even even though you're going to throw the projectile at an angle theta or at an angle of 90 minus theta. I repeat, horizontal range of a projectile. Okay, horizontal range of a projectile remains the same. It remains same whether the projectile is thrown at an angle theta at an angle theta with horizontal or at an angle of 90 minus theta. Okay, or at an angle of 90 minus theta. Okay, so whether you're throwing with angle theta or whether you're throwing with angle of 90 minus theta, the horizontal range remains unaffected. So this is a point that needs to be kept in mind. Okay, so this is one important point. So similarly, some points are there. Now, if horizontal range is n times, I repeat, if horizontal range, instead of writing it, horizontal range, I'll put it as R, children, because R is understood as horizontal range. For simplicity, I will use R. Okay, if R is n times the maximum height, if R is n times, okay, the maximum height, fine. In that case, what is going to happen? So we will see. If R is n times the maximum height, that means you go and relate horizontal range as R is equal to n times h max. So this is what we are trying to relate. Go and substitute the value of R, horizontal range relationship. So you know that horizontal range has got the formula u squared sine 2 theta by g. Substituting it, u squared sine 2 theta divided by g equals n times h max. The maximum height, that also we wrote down the formula as u squared sine square theta divided by 2g. So we got a relation like this, right? This is what we wrote. Now you simplify it. You know that both the sides u squared gets cancelled off. G and G is also getting cancelled off, right? Now, what's happening here? Sine 2 theta, I hope you guys know from trigonometry, sine 2 theta can be written as 2 sine theta cos theta. Okay, so I'm going and substituting that value there. So you can write this as 2 sine theta cos theta equals n times sine square theta. So sine theta and sine square theta you can cancel. So one sine theta term will remain. Okay, so that is going to remain there. Not to forget, at the bottom there is a 2 here on the right hand side. So now I want to relate in terms of the angle tan. So 2 and 2, if it goes to the left side, 2 times 2 becomes 4. So I will get 4 cos theta is equal to n sine theta. I hope you guys know that sine upon cos is tan. So sine theta by cos theta is tan theta. So I can write 4 equals n tan theta. And you get the relation as tan theta is equal to n upon So this is how you can relate angle theta with the number of times. Okay, if n number of times, if you're trying to relate for the projectile, so if it is n times, you can relate it in terms of theta as tan theta equals n upon 4. This is an important result to solve numerous questions. Okay, so that's the reason I am emphasizing on this. Fine. So tan theta is n upon 4. With that, we'll move on to the next aspect. The next important point, let us discuss. Now, for the next part, when horizontal range is maximum, then you try to relate what is time of flight. Okay, when horizontal range is maximum, then time of flight is, so we'll see what is the time of flight in that particular case. Okay, so you all know that we have learned the expression for time of flight as t is equal to, that is tf is equal to 2u sine theta divided by g. This was the formula that we learned. Okay, so now here you go and substitute. You know that theta is going to be 45 for maximum, right? When maximum horizontal range is there. So what will you do? You will take theta is equal to 45 degrees. If you substitute theta is 45, what happens to this expression? You will get tf is equal to 2u sine 45, which is 1 upon root 2. So you can write it as 2u upon root 2 times g. And children, you go for rationalizing. I hope if you rationalize the denominator, you will be getting time of flight tf is equal to under root 2u by g. So this is the expression. If you multiply and divide by root 2, basically. Okay, that's how you rationalize the denominator. So this is the expression for time of flight when the horizontal range is maximum. So this is one important relation again. Okay, next condition. So like this we have different conditions. The next condition, let us see. Okay, again, when horizontal range is maximum, we will see what is the maximum height. When horizontal range is r, so I am representing using r. When r is maximum, then the expression for maximum height the expression for maximum height. So how do you write down the expression? You can write h max is equal to formula. You first will write the formula, which is u square sine square theta divided by 2g. Okay, so this is a formula, children, for maximum height. But you know that for maximum horizontal range, theta is anyways going to be 40. So if I go and substitute, in that case, this expression gets reduced as u square upon 4g, because 1 by root 2 the whole square is 1 by 2, and 1 by 2 multiplying with the 2 which is already there becomes 4. So 4g, u square by 4g. Okay, but you know that u square by g is r max, which we already related before. I hope you remember. Previously we already related r max as u square by g. Can you see? So we will go and substitute in place of u squared upon g as r max, or maximum horizontal range. So finally you get the relation as maximum height equals r max upon 4. This is the relation between maximum height and maximum horizontal range. Again, this relation is important for solving certain type of questions. Okay, so this is the next relation that we have got. Fine. Next, so moving on. So like this, we have different relations, children. So I hope you're making a note of it. So, and then we have the next aspect. Let's see what is the linear momentum. So we are seeing what is the linear momentum of projectile. So linear momentum of projectile at maximum height. So we'll see what's the linear momentum of the projectile at maximum height. So what is linear momentum? So I hope you guys might be knowing momentum is given by the formula P is equal to product of mass into velocity. So that is the general expression for momentum. So when I say linear momentum at maximum height, so again we go and express here. So ph, p suffix h means linear momentum at maximum height. So we write this as mass into velocity. So here when I say velocity, it is a vertical component of velocity. So it is u cos theta. So mu cos theta is the linear momentum at maximum height. So this is again another relation to find out what is the momentum. Okay. So like this, we will use the relation to find out momentum in questions that demand us to calculate what is the momentum. So use this particular formula and you will find. Similarly, you should be knowing what is the kinetic energy. Okay, so kinetic energy of the projectile. Kinetic energy of the projectile at the point of projection. Projectile at the point of projection is given by the formula. So even at the point, that is when it is being projected, obviously you know that it possesses kinetic energy. So it's given by half m times u squared. Okay, so you write it as half m u squared in the place of u. Okay, so you can go and substitute the value as u cos theta. So when I substitute in the place of u cos theta, you will get half m u squared cos squared theta. Since you have substituted u is equal to u cos theta. Okay, the horizontal component. So you will find out the expression for kinetic energy as half mu squared cos squared theta. This is also an important relation. So this is necessary whenever kinetic energy is asked. Okay. Similarly, the last part of this we will see, which is the angular momentum. So moving on to the next aspect. Angular momentum. So let me scroll. Angular momentum when the projectile angular momentum when the projectile is at the maximum height. Of the projectile. So angular momentum of projectile when it is at maximum height. So that is also given by certain relation, children. So angular momentum is given by the symbol L. So L is the symbol at maximum height, so we can keep it as LH. Okay. So here we can write the formula for angular momentum first, which is mv into h, because at height we are saying, so mvh. Okay. M is nothing but mass, so you keep it just like that. But what is V? V is nothing but the velocity component, so you will write it as u cos theta. What about height? Height formula to be substituted, which is u squared sine squared theta upon 2g. So this is what you will get, children, for angular momentum. It's a combination of three different terms: mass, velocity component u cos theta, and height, which is u squared sine squared theta upon 2g. So we can express like this. Now this can further be simplified. How do you do that? So here you can see that u times u squared can be written as u cubed. So can be expressed as m times u cube times here okay, upon 2g, that also I will write, divided by 2g into, you can see that there is cos theta into sine square theta. Now how can we simplify cos theta into sine square theta? I hope you guys know that sine 2 theta is 2 sine theta cos theta. From mathematics you might be knowing. Here what I want is, I basically want, I have cos and I have sine theta term as well. Okay. So what I'm doing, I'm multiplying on both the sides with sine theta. So upon doing so, see, you can multiply or you can also retain, because I hope you guys know that cos into sine into 2, is definitely sine 2 theta, right? So this particular term you try to bring in that particular form. Okay. So when you try to bring in that particular form, so what am I going to do basically is, I'm multiplying and dividing with 2 for this expression. So into 2 divided by 2. So when I multiply and divide by 2, what happens to this expression now? You can see that 2 sine theta into cos theta becomes sine 2 theta. So I will write this as m u cubed divided by 2 2s are 4g into 2 sine theta cos theta. I am writing it as sine 2 theta. So sine 2 theta into, there is one more term which is left, which is 1 sine theta term additional. So you can write it as sine 2 theta into sine theta. Okay. So that is the final expression, simplified version of angular momentum. So mu cubed times sine 2 theta times sine theta upon 4g. So you have the expression now like this. Okay. Yes. So this is the expression for angular momentum at maximum height. So let's box it. So either you can use this or you can also make use of this formula as well. Choice is yours. Totally, it is purely based on the given data. So if you would like to use the first one also, you can use, or this one also. So better to use the simplified version so that you can arrive at the answer even much faster. Okay, you can save time. So that is the reason we simplified it and we have it as a ready-made formula, so that we can use them to solve numericals proactively. So on that note, so here we are coming to the end of projectile motion. So with that, projectile motion part is done. So now what we will do, we will try to visualize projectile motion. Obviously we have done theoretical aspect, we have now learned. We will try to visualize this using an animation. So I'll take you back to an animation and window. So we'll try to see the animation, and also there is an interesting simulation which is there. So I'll show you that as well. Okay. So hang on. So let me start sharing that screen also. It's getting loaded. We will go to the animation screen for projectile motion. Yes, children. So I'm sharing it now. I've started sharing. So let me know if you're able to see it. Yeah, I hope it's visible now. Okay, so let me play it. I hope you'll be able to hear the audio as well.
Suppose you and your friend are standing at the edge of a cliff. Your friend drops a stone straight down, and with great speed, you throw a similar stone horizontally. The question is, which stone will land on the water surface last? Does your intuition tell you that since you threw the stone with greater speed, the stone will take more time to land? If so, you are wrong. Both stones will actually land at the same time. Welcome to the interesting world of projectile motion. Let's go over some fundamental concepts. When you throw a ball at an angle, it never goes straight like this. Instead, it will have an elegant curved path, more specifically, a parabolic path. This kind of projectile motion happens due to the effect of gravity. When thrown at an angle, the object has two components of velocity, one horizontal and one vertical. The gravitational force always acts vertically. When a force acts on
So here, I hope now it is clear when you try to visualize things. So when a projectile is being thrown, could you see there was a parabolic path that it took, right? And here they have shown, two different arrow marks which are coded red and blue. The red arrow mark is the vertical component, and the blue arrow mark represents the horizontal component of the projectile. Okay? So this is very important because you have to visualize this. So that's the reason I'm showing this animation video. Okay, so pay attention to it, children. Now you will be able to. It will be easy for you to correlate the concepts that I've taught, in the theory part. So pay attention. So it's an interesting animation. We'll continue.
On a moving object vertically, the horizontal component of velocity never changes. Only the vertical component of the object's velocity will change due to the vertical force. Therefore, the initial horizontal component of velocity you have given will also not change throughout the motion of the object. Let's analyze this more closely and
yes, I hope it is clear why the vertical component only changes and why not the horizontal component. That is because, any idea why is the vertical component changing and not horizontal component? What is the reason behind it? I hope it's quite evident from the animation video. Yeah, anybody? What is the reason when you throw a ball upwards, why the vertical component changes? Initially, you could see it reduced. At the highest point, it almost became zero. Did you observe it? That arrow mark, red arrow mark, it reduced, it became zero at the highest point, right? And after that, it started increasing. Why do you think is this observation, happening this way? What is the reason behind this observation? Yes, it is there in the motion of the ball itself. When an object is thrown, it goes up and then comes down in a parabolic path. So the answer lies there. Why? No idea? It is because gravity is pulling the object downwards. At each and every point, gravity pulls it. Initially, when you're going to, project it with some velocity, at each and every point on its path, gravity is doing its job, right? If gravity wouldn't have been there, it would have gone into outer space. That's a different story. Because we are living in a planet which has gravity, at each and every point, the gravitational pull of the Earth is going to be felt by the object. And therefore, the red arrow mark magnitude keeps reducing. As it reaches higher point, eventually it becomes zero for a small duration of time. And then it starts increasing as it falls down. Okay, so that is the reason, children. So moving on.
see how the variation of the vertical component of velocity affects the shape of the trajectory. The horizontal and vertical distance traveled by the object for a small time interval is shown here. Its complete motion will be as shown. Since the horizontal component of velocity does not change with time, with an equal time interval, the ball will travel the same distance horizontally. However, the vertical component of velocity has been reduced due to the effect of gravity. Thus, the distance traveled vertically in this time interval will be lesser. Just continue this logic for a few more intervals. You can clearly see the object is taking a curved path. As the vertical velocity keeps on decreasing as the ball travels up, the point where the vertical velocity becomes zero will be the maximum height it can achieve. After this point, the vertical velocity will become negative, and the object will start its descent. During the descent, the gravitational force and velocity are in the same direction, so the vertical velocity will keep increasing. This will be the final shape traced by the ball. The shape of this trajectory is known as a parabola. Here's an interesting thought experiment. This cannon is ejecting a ball perfectly vertically. The ball will come back to its initial position, or zero movement, in the horizontal direction. Now, let's reduce the angle and eject it with the same speed. Now, the ball can travel horizontally. With a little more angle reduction, the range increases further. When the cannon's angle is down to 45 degrees, the range becomes even higher. However, if you increase the angle after 45 degrees, the outcome is different. The range actually decreases. The maximum range is at an angle of 45 degrees. Before and after that, the range decreases. Can you guess the reason behind this? The range of the ball is multiplication of the initial horizontal velocity you have given, multiplied by the time duration it stays in the air. The time the ball spends in the air decreases as you decrease the angle. However, the horizontal velocity keeps on increasing as you reduce the angle. Multiplication of two numbers will be maximum when both the factors have a good value. In this case, the time the ball spent in the air and horizontal velocity has a good value at the angle of 45 degrees. This is why you get maximum range when you throw the ball at 45 degrees. With this understanding of projectile motion, it becomes quite easy to solve the question we posed at the beginning of the video. The time it takes for the stone to hit the ground depends only on its vertical velocity. Even if you have given a high horizontal velocity to your stone, its vertical component is zero. This means both the stones have the same vertical component of velocity at the beginning, zero. This velocity will increase over time due to the effect of gravity, but with the same magnitude. This means the vertical component of velocity of both stones is the same throughout their travel. Therefore, both will hit the ground at the same time. Pretty interesting, right? The greater speed you have given to the stone has no effect at all on its travel time because you threw the stone perfectly horizontally. Thank you for watching. We hope.
Yeah, I hope now this animation, is useful. It's an eye opener. So based on this, the concept of projectile motion is even more clear because you try to visualize it. Okay, so that's the reason. So I was about to show the simulation also. The simulation is also very similar to the video. So it's the same aspects, based on the time taken by the projectile, we can find out when is the horizontal range going to be maximum and when it is minimum. So all those aspects have been covered here itself. Okay, so now we will go back to our window. Let me stop presenting and then let me represent. Yeah, I started presenting the window again, the previous window. Okay, so now we have learnt about the different aspects of projectile motion in detail. So that is done in detail. So we have looked at this in detail. So on that note, so we will start solving questions, okay, based on it, children. So let us see the questions now. Okay. So now we'll see questions, practice questions. on projectile motion. Okay, practice questions on projectile motion. So we'll start seeing them one by one. The first question here, we go. Okay, first question. A projectile is thrown with an initial velocity of v vector v is equal to, it's given in the vector form, p I cap plus q j cap. Okay, p I cap plus q j cap. If the range of the projectile is double the maximum height reached by it. Okay, is double the maximum height reached by it. Then which of the options are right? Option A, so I'm giving you the options. P equals to Q. Option B, Q equals 4P. Option C, Q equals 2P. And option D, Q equals P. Okay, these are the options. So read the question carefully, try to analyze and then interpret what is the answer. Okay, just try it out, give it a shot. It's worth trying. So projectile is thrown with initial velocity. They've given you the vector form of it. So V is equal to Pi plus Qj is given. Okay, so these are the relations. Yes, children. So first aspect, you will have to find out what is the magnitude of the velocity, because whenever you have a vector form, finding magnitude is the first aspect, because they've given you the vector form of velocity. So what is that? It is Pi plus Qj, that is given. So what is the magnitude of vector? So find out the magnitude. So it's under root of squares of the components of I and j, which is under root p squared plus q squared. That is the magnitude. So once you have the magnitude with you, so now based on the angle of projection, so you can say that the angle of projection, you can assume it as theta, because always for projectile motion, projectiles are projected at a particular angle, right? So let that be theta. Let angle be theta. Okay, so because the angle of projection is theta, so how can we relate it with respect to P and Q is what you will have to identify. So I hope it was very clear from the animation video also, and I also have shown you. So whenever the projectile is projected with some velocity v, it will have two different components, right? So it will have one vertical component and it will have one horizontal component. Vertical component we will call it as Vy, and horizontal component we will call it as Vx. So when there are two such components, and if this is the angle theta, so you can basically use trigonometry and try to relate what is, the theta with the values p and q from our given vector. You know that horizontal component and vertical components are already specified. Okay, so what is the horizontal component? It is vx, which is equal to p, and vertical component vy is equal to q. These both have been specified already in the vector. So which ratio can be used to relate theta, p, and q? You can see it forms a right angle triangle, right? So if you see, there is a right angle triangle that it forms. If you're extending this, you have a right angle triangle. So in this right angle triangle, vertical component is vy, horizontal component vx, and this is your angle theta. Okay, so you know that the trigonometric ratio that relates opposite and adjacent side is going to be tan ratio. So don't you think tan theta can be written as vy upon vx? Yes, you can write it. Okay, I mean vy upon vx. Let me just change it. So vy upon vx, opposite upon the adjacent side. You know that vy is p, so we can write it as, so appropriately can be expressed as p and q respectively. So here they have taken as p and they have taken it as q, right? So appropriately it can be expressed. So vy is q, so can be written as q by p. So this is one important relation that now we have got. So let me box it and keep. So we have tan theta, we got the relation as q divided by p. So let us have it. One relation. Now here they are telling, according to this question, you can see that there is a relation. What are they saying? The range of the projectile is double the maximum height. So use that relationship. They are saying range is represented. So let me write as range is double the maximum height. So how do you write this mathematically? You can write this as r is equal to 2h. Okay, so range is equal to double the maximum height. So the formula for range, you all know the formula for range is nothing but u squared sine 2 theta divided by g, twice the maximum height. So 2 into maximum height formula, which is u square sine square theta divided by g. Okay, that is 2g here in this case. Okay, so u squared sine square theta divided by 2g. So you will get a relation like this. Now simplify this. G and g you can cancel out. Here 2 and 2 you can cancel. U squared and u squared also. Basically you can cancel. But here we are not cancelling. The representations. Okay, you can cancel it. We can cancel because anyways it's like terms, right? So need not go and substitute there ux. Even then also it will get cancelled out. Fine. Then now once you have cancelled out these terms, what are you getting? You will get sine 2 theta is equal to sine square theta. Expand it, simplify it further, which means, so here sine 2 theta can be written as 2 sine theta times cos theta equals sine square theta. So you can see the left hand side and the right hand side, you can cancel out one sine theta terms. So when you cancel out, you will get 2 cos theta is equal to sine theta, and you will get the value of tan theta as 2. Okay, because sine by cos is tan. So you get the value of tan theta as 2. So if tan theta is 2, previously you know that tan theta is q by p. Relate. This I'll mark it as equation 1. this I'm marking it as equation 2. So if you relate 1 and 2, you get that 2 is equal to q by p, which means q is equal to 2p, and that is our relation. So you got q is equal to 2. Okay, so which option says q is equal to 2p? You can see that answer is option C. So third option, q is equal to 2p is the right answer. Fine. So that's how you solve this particular question. Okay. So this question, it's a different approach, children. That's the reason I discussed. So where question. Fine. So analyze it. So try it, children. So you have to do these questions first. Even before you touch the questions, go through the concepts that we have learned for the day, and then try solving them one by one. Okay, that is when you will get it. So all the concepts, formulas should be in your fingertips. So write down all the formulas. There are so many formulas that we learned. So mention them. As I always tell, so maintain a separate formula notebook, and then start practicing the questions one by one. So that way, it is you are well equipped, as well as you can think which formula would be a wise choice to solve the question. Okay. And some questions you will have to relate them halfway, and then you will have to equate them. So as in we have done in this question. So these questions are where you have to simplify, apply some mathematics also, and then relate. Okay, that's it, children. So with that we can wind up. So any doubts you can ask. Okay, so definitely I'll revert back. I'll post these notes also. I'll send it to sir. Sir will be posting it. Fine. Yeah.
Thank you, Manish.
Okay, welcome.